There's homework due tonight, and then I will post one more homework today, due in 1 week, and then after that we take a test. And my plan is to take a small break after class and then make the next homework, which is homework 4, 5, 3. Let's see, 1, 2, 3 was for test 1. 4, 5, and 6 are for test 2. The lecture today is counting and only counting, and I've picked 3 techniques. There's a few more out there, but we're going to focus on the multiplication rule, combination, and permutation. I'm going to go back over the multiplication rule, and we're going to do a couple examples. Oh, that looks crazy. We talked about having m ways to do x. And n ways to do y. Then we have m times n ways to do x and y. So what we're going to do for this next example is start with rolling a die and then flipping a coin. How many outcomes are possible? And then you'll see today that I like to make a placeholder for all of the different things I'm doing when I have a multiplication rule. So the first thing I want to do is flip the coin. And then I'm going to have a place to have the roll for my die. There are two outcomes possible for a coin flip, heads or tails. Two choices there. Then out of the die, there are 6 faces. You can choose from 1 through 6. So 6 multiplied with 2 is 12 outcomes total. 2 times 6 ways to flip a coin and roll a die. I still want to talk about these outcomes, so we're going to draw a tree diagram. So for this, you have a starting place. And in this experiment, we start with the coin flip, heads or tails. Okay, and if you flip heads and then you roll a die, after that, there are options 1 through 6. And the same thing if you have tails and then roll a die, the choices are 1 through 6. So you get each outcome by following the branches. You can have heads, then 1, heads, then roll 2, flip for heads, roll a 3, and then so on. Go from tails and then roll a 2, tails, roll 3, wait till tails and rolling 6. Gives you 12 possibilities. This time, we want to flip a fair coin 7 times. How many outcomes are possible? For every trial, which there's 7 total, I'm going to have a placeholder. And 1, 2, 3, 4, 5, 6, 7. Okay, so I do my first flip, and it can be heads or tails. So those are 2 choices. Multiplied with whatever happens in the next flip, which is the same coin, heads or tails. It's 2 choices for all of the flips that we do. So every time it's heads or tails. Multiplied with each other, which would be 2 to the 7th. And it turns out to be 128. And one more example where we're talking about a password. A password is made of 3 digits, 0 through 9. And then followed by 4 letters, A to Z. How many passwords are possible if the digits and the letters can be repeated? And by the way, in this kind of problem, lowercase is the same as uppercase. So there's nothing special about little a and capital A. Okay, how many passwords? Let's see. Okay, we're using the multiplication rule. By the way, I'll try to remember when I talk about permutations and combinations. Both of those examples are when you make a choice without replacement. So you take something from a set and you don't put it back. You remove it from the set. It's not replaced. Just keep it. However, this time, if it's repeated, you can replace it. So if I use, let's say you use the number 2, and my next trial, I can put 2 back and choose 2 again. So if you see that it can be repeated, you will use the multiplication rule. If it says like not repeated or without replacement, you're probably looking at a combination or a permutation. Okay, we have 3 digits. Let's make 3 spaces. And then 4 letters. So for letters, make them a little more bold. Okay. In the first spot, we pick one of the digits 0 through 9. 0, 1, 2. Count all of those possibilities, and there's 10 choices. And then since you can repeat a digit, I have the same 10 choices. And again, there are 10 digits I could choose from for this spot. Now we're getting to the letters. I can pick between A and Z. And then I've checked, there's 26 letters in the alphabet. So you have all 26 to pick from. And since you can repeat a letter, you still have 26 choices here and here and here. Okay, almost put everything together. So you get this 456,976,000. For permutations and combinations, I'm going to put up a short version of what each means, and then we'll do the definition, and then we'll just practice examples. If it's a permutation, then order matters. You're going to select different values in a certain order, which means that something like event AB is different than event BA. If it's a combination, order doesn't matter. The idea will be that you choose a few objects out of a set of objects in any order. The order doesn't matter. Just pick a couple things out of a set. And something like AB is the same as BA. And then before we go over the full definition for each of these, I need to talk about what a factorial is. So we need to stop and do that on the side. Okay. The factorial of n is written as n, and it's an exclamation point, but in math it's called n factorial. So it looks like this, read as n factorial. And it is the product of all integers between 1 and n. Okay, so we're going to write this mathematically. N factorial is the product of all integers less than n until you get to 1. So we're going to take n, multiply with n minus 1, times n minus 2, times n minus 3, until you get to, if you have it, the last few, 3 times 2 times 1. Let's start with 1 factorial. Would be 1, just 1. And 2 factorial. 2 times 1. Three factorial. Is 3 times 2 times 1. Six. Okay, find 4 factorial. Yeah, 4 factorial is 4 times 3 times 2 times 1. Should be 12 times 2, which is 24. All right, let's go to 7 factorial. It is 7 times 6 times 5, all the way down until you get to 1. And I got 5,040. Let's look at 9 factorial. We want 9 times 8 times 7, 6. No. Times 2 times 1. And I got 362,000. 880. Okay, and then there's this last one, which you may come across sometimes, and there is a proof, but we're not going to go over the proof. But if you ever see 0 factorial, it just so happens to be equal to 1. Okay, so now we can put up the definition for permutation. And these are permutations without replacement. So we're selecting a group in order, and we don't replace those objects back into the group. Just take them out of the group, keep them selected. Again, permutations, word order matters. We're going to select R objects out of N total. And we're going to look at permutations without replacement. The number of permutations is denoted and by the way, these are permutations of the R objects selected out of N objects. So this number is written as subscript n, and then permute with a capital P, and then back to a subscript r. It says out of n, permute r, which means we're taking r objects and selecting them in a certain order from n total. And then you can find that number with this formula. We put n factorial in the top, and then divide by n minus r factorial. So first I want to get used to this notation, and later we'll do examples of needing to use permutations. It says 5 permute 2. Five permute 2 is 5 factorial. Divide by 5 minus 2 factorial. Then I've got 5 factorial over 3 factorial. Let's expand the numerator. And then I want to write out 3 factorial. And I have the number over itself, it reduces to 1. So 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1, and 1 times 1 times 4 times 5 is 5 times 4. Simplify 6 permute 1. Six. And then permute 1 would be 6 factorial. By 6 minus 1. That's 6 factorial over 5 factorial. So I'm going to expand numerator. And then same thing in the denominator. Write out 5 factorial. And when you have 5 over 5, it reduces to 1. The same for 4/4, 3/3, 2/2, and 1/1. So all you have left is 6 times 1, which is 6. Okay. A combination is an unordered selection of R objects out of N objects without replacement. And again, we take these objects out of the group and we don't put them back. So it's without replacement. Right. The number of combinations are out of N objects. This is written in a similar way. We're going to use out of N total, subscript N. We use capital C for choose. Choose R. From N, choose R. And choose R is equal to N factorial and divide by R factorial. And that's multiplied with N minus R factorial. Out of 9, we want to choose 4. So also you can see this as I'm taking 4 objects and selecting them out of 9, and the order doesn't matter. Just take any of the 4 randomly in any order out of 9. And the possibilities are going to be 9 factorial over 4 factorial. Multiply that with 9 minus 4. So it's a 9 factorial over 4 factorial times 5. So I'm going to expand all of my factorials. By the way, a place where you can type this in is called Desmos Scientific Calculator. So if you Google Desmos calculator, you can type this in, it will give you the result. Or you can just keep working through it on scratch paper. We've gotten to 9 times 8. It's and 4 factorial, I'm going to keep in parentheses. Same with the 5 factorial. And I want to work on this part and also the numerator. So I'm going to use this 5 over 5, simplifies to 1. Same with the 4 over 4, 3 over 3, 2 over 2. Let's see what's left. 9 times 8, 7 times 6, over 4 times 2 times 2 times 1. I don't really need to multiply by 1 because it keeps the number the same. So I'm going to use the 3 times 2 and simplify that with 6. So there's 9 times 8 times 7 over 4. And I looked at 8 divided by 4. It reduces to 2. So I have 9 times 2 times 7. And that is 126. We are looking at 8. Choose 2. Start with the formula. 8 factorial. It's over 2 factorial times 8 minus 2. So we're going over here, and I've got 8 factorial over 2 factorial times 6 factorial. And then you can either use a calculator or keep using scratch word. I'm just going to put down what my result was. Oh, okay. After doing my own scratch work, which we could do, but I'm kind of a little tired, we're going to go with the answer of 28. So this wouldn't be too difficult to expand and then reduce and then simplify till you get to 28. But another way to check maybe is to use a calculator. I suggest Desmos. Scientific. Calculator. That's a place where you can type this in and you'll get that result. And you can just find this on Google. Okay, now we want to look at actual experiments and find all outcomes. So from the first one, we have a pond and we select a group of fish. In how many ways? Can I select 7 fish? I'm taking these out of a pond that contains 30 fish. So when you make this selection of 7 fish, the order doesn't matter. So it doesn't matter in which order you pick them, you just group them together and take them out. So since order doesn't matter, I want to use combinations. It's going to be out of 30, we would like to choose 7. Which would be 30 factorial over 7 factorial. Multiply with 30 minus 7 factorial. Okay. We've gotten to 30 factorial over the 7 factorial times 23. That. $2,035,800 traces. Next, we have 9 swimmers who compete in a race. How many ways can I place first or second or third? Okay. And there are 2 ways to think about this. First way is that I have 9 swimmers. I want to pick 3 of them and put them in a certain order, first, second, third. So order would matter. That means use permutations. And what we're looking at is from 9, we want to permute 3. Okay, which means we take 9 factorial, divide by 9 minus 3 factorial. We have 9, 6, which is 9 times 8 times 7 times 6, it's 5 times 4, 3 and 2 and 1 over 6 factorial. 6 times 5 times 4 times 2. Okay, there's 1 over 1 and 2 over 2, 3 over 3, 4 over 4, 5 over 5 and 6 over 6. And what's left is 9 times 8 times 7. And that is 504. Okay, There's another way to think about this. You can use the multiplication rule, but you have to use it very carefully. So okay, so let me talk through it. So I'm thinking about having 3 spots. First place, second place, third place. Okay, so the swimmers are coming and they cross the finish line or something like that. And the first person who gets first place, there are 9 choices there, 9 people to choose from for that first spot. Okay, but then we give that person first place and they move to the side, and what's left are 8 people to choose from for second place. Okay, out of those 8 people, we have 1 person who has second place, and then third place, we have 7 people left to choose from. So after carefully thinking through the multiplication rule, I get to the same kind of result with permutations. 9 times 8 times 7, which is 504. Okay, let's try another. We have 5 prizes to distribute to a random group of 21 people. The rule is that every person can only get 1 prize. How many outcomes are possible? So in how many ways can I choose a group of 5 people to give prizes to out of 21 people? Well, this group of 5 people doesn't matter what order they're in as far as giving them prizes. Everyone gets a prize just the same. And when order doesn't matter, it means use combinations. Okay, I want to do the total, the 21 people, and then from them we choose 5. Okay, this would be 21 factorial divided by 5 factorial multiplied with 21 minus 5. 21 factorial over 5 factorial. 16. Which at this point I could, and I think I did, type it into Desmos, and then I got this result of 20,000. $349. I'm pretty sure this is our last problem, and we're going to put it in 2 parts. So the problem is about a lock, and it has rotating discs to open it. There are 4 rotating discs. Each has the digits 1 through 9. How many different lock codes are possible? If, then for part A. First part, you cannot repeat. Let's see. A number can be repeated. Okay, so especially when you see that you can use repetition, you're going to go for the multiplication rule. If it says without repetition, you can carefully use the multiplication rule or use a permutation. Okay, so we have 4 discs. And for each, I can choose 1 through 9. Which means I've got 9 options here. And then for my next disk, I can repeat one of those numbers. So it's another 9 options on each of the disks. 9 to the 4th is 6,561. This time, a number cannot be repeated. So since it's without repetition or without replacement, I could use permutations. Since I'm going to have 9 possible digits and then put them in a certain order, for the 4 spots on the lock, and that will open the lock. Which, by the way, the locks that you had on a locker really should have been called a permutation lock, because a combination lock order doesn't matter. But when you open those locks, the way in which you put the numbers in, it does matter what order you do. So just note to self that even though the combination lock is where order matters in like real life, in mathematical terms, combinations are for when order doesn't matter. When you need to unlock a lock, order matters, use a permutation. Out of 9, permute 4. This is 9 factorial. Over 4, oh, it's over 9 minus 4 factorial. 9 factorial over 5 factorial. We're going to expand. The 9 factorial is 9 times 8 and 7 and 6. 3, 2, 1. And then our 5 times 4 times 3 times 2. Reduce 1 over 1, 2 over 2, 3, 4 over 4, 5 over 5. And what's left is 9 times 8 times 7, 6, which is 3,024. And then the last note for today is that I could use the multiplication rule, but you need to be very careful when you think through what's happening. Okay, So I have my placeholders for each part of the lock. So this is just another way to get the same answer. You can pick whichever way you like. So I've got 4 spots, 4 dials to put in the code. In the first part, I've got 1 through 9 to choose from. So I've got 9 options. And once I pick one of those digits, I can't use it again. So in this place, I only have 8 digits to choose from. And then from those 8, I choose one, and in the next spot, I only have 7 choices. After that, we've removed one of the choices from 7 and what's left 6 choices as, or 6 choices for whatever the last digit is. So you end up with the same product and the same number. Okay, we're going to end there for now. I do have more examples, which we might do next week, but I want to start to use counting to find probabilities. So we may save the counting practice for a review week. Oh, sorry, we're done. Okay, thank you everyone. Have a good weekend. I'm posting homework today, so keep up with homework. Okay, and we're good. Bye everybody.